In this video, we're going to do an AP Physics 1 FRQ QQT type, number 3. So we have a container is partially filled with water of density of water. A sphere with a density S and radius R is held under the water by a string with negligible mass, which is attached to the bottom of the container as shown in figure 1. The dot in figure 2 represents the sphere, and the sphere is attached to a string. We want to draw and label the areas for the FBD. So on the sphere, we're going to have a buoyant force that is acting upward. We're going to have a weight force that is acting downward. And we're going to have a tension force that is acting downwards as well. So our weight and our tension are both pointing down, so we're drawing them side by side. Now, we are asked, when the string is cut, the sphere rises upward in the water. Draw the forces from the water, or the drag forces from the water are negligible. Starting with Newton's second law, we want to derive the expression for the acceleration of the sphere immediately after the string is cut. So, what forces do we have left? At this point, we have our weight that's still acting down, and we're still going to have your buoyant force that's acting up. So we are only having forces in the vertical direction, so we're doing Newton's second law in the vertical direction. We have buoyant force acting up and weight acting down, using this as our axes is equal to mass acceleration. We know our buoyant force is equal to rho water GV. And this is the volume of the displaced water. So if we substitute this into our equation, here we can write density of our water, GV. Now, we know that mass of a sphere is equal to the density of the sphere times V. That's because density is equal to the mass of the sphere divided by volume, and we just rearranged that. We also know the sphere volume formula is equal to 4/3 pi radius cubed. So we can take this expression for our mass and substitute this in. We're going to have density water, G times V minus density S, Vg is equal to density S, Va. After this, on the left side, we can factor out our G and V here, and we have a G and V here. So we have density of water minus density S is equal to density S, Va. We can cancel out that V on both sides. We still have a G here. So A is equal to G, density water minus density S, all divided by our density S. So you could also factor out that G from everything, leaving you with this, density S minus 1. So our acceleration is going to be upward because we have a positive value. Now, on the axes shown in figure 3, sketch a graph of the velocity of the sphere as a function of the vertical position of the sphere in the container starting from the moment the string is cut until the top of the sphere reaches y is equal to h. We know that immediately after the cut, we have v is equal to 0. Therefore, our sphere is going to accelerate up while it is fully submerged. So your velocity is going to increase because we know our acceleration is constant while our object fully submerged. We use the kinematics equation. V squared is equal to V initial squared plus 2ay. So we have V is, this simplifies down to V is equal to the root of 2ay because this is equal to 0. And then you just take the root of both sides like that. So we know that we're going to go from y is equal to 0 to y is equal to h. We're going to draw a curve that starts at the origin, and then it's going to bend and decrease concave down because we have the square root graph. It's not going to be a straight line because our velocity is proportional to the square root of y, not just plain y. Now, the sphere rises to the surface of the water, traveling the distance h in time t1. In a similar scenario, the sphere is again released from rest at a distance h below the surface of a liquid with a density L, where density L is greater than density water and resistive forces from the liquid are negligible. The sphere travels a distance h through the liquid in a time t2. Explain why t1 is greater than t2. So when you are in the second liquid, you have the density of the liquid is greater than the density of water. We know that, again, our buoyant force is equal to the density of the fluid, g times the volume displaced. So that means that our denser liquid gives a larger upward buoyant force, since we see that our density is directly in that equation right here. Now, we can see that the weight of the sphere is equal to mg, which is equal to density S, Vg. And this is unchanged. Therefore, the net upward force is larger, since this is going to equal to your buoyant force acting up minus your weight. So when you solve for your acceleration, it's going to be larger, since your net force is going to be larger. And you're going to divide F net, a larger F net, by the same mass. So when you have the same h starting from rest, your kinematics equation is simplifying to h is equal to 1/2 at squared. So if you have a large a, that means you have a small t. So that means that T1 is going to be greater than T2. This makes sense because if you have a denser liquid, that produces a greater buoyant force, so the sphere accelerates upward faster and reaches the surface sooner.